All right, hello everyone. Today's topic is randomness in cryptography. Something very important, but something almost all the time overlooked. Okay, so this is very, very important because we need randomness in cryptography a lot. And in order to understand what it is, we have to know what a random means and how we can generate random numbers or random bits and so on. Because every secret actually should somehow generated in a random way. All of the secret keys, if you are not generating them from a password, then they should be generated randomly. So let's start. Cryptographic algorithms require random numbers for parameters like keystreams of one-time paths, secret keys of a symmetric cipher system, public key parameters, session keys, nonce, initialization vectors, and solves. So as you can see, this, of course, this is not the full list. In almost every public key algorithm, in the pseudocode, you will see that randomly generate a number or sometimes randomly generate a prime number and so on. So we have to have a way of generating these numbers in a random way. Okay, so this leads us to the concept of random number generators, RNGs. An RNG produces a sequence of numbers on an interval between min and max. So, if you want to generate a number of digits, so this min can be 0, max can be 9, and you can generate digits of any integer this way. Or if you're generating bits, your min will be 0, max will be 1. Of course, you will be generating integers, not real numbers in that scenario. But of course, you can have a different random number generator which generates real numbers and so on. So we want an RNG to have the following properties. These are statistical independence, uniform distribution, unpredictability. So I will give these definitions in a minute, but cryptographic algorithms mostly require random bit generators. In other words, min will be 0 and max will be 1. In most cases, but of course we will talk about for the general case where we have a random number generator, not a random bit generator. All right, so let's start with the first property, statistical independence. For a given generated sequence of values, a particular value should not be more likely to appear next. This is very important. So assume that you have a random number generator and you produce millions of numbers, digits. So by looking at the previously generated sequence of values, you shouldn't have any advantage of guessing the next value. Okay, so this is what we call statistical independence. Second thing is that uniform distribution. All numbers are equally likely and none appear more frequently within the output. So this is very important. If you are, for instance, generating only zeros and ones, generating a 0 should have a probability of 1/2, and generating 1 should have a probability of 1/2. Similarly, if you are simply generating digits, which is numbers from 0 to 9, we have 10 numbers. So any one of them should have probability of 1/10 to appear. Okay, so this is uniform distribution. Third one is unpredictability. So this is what we want in cryptography too. An attacker should not be able to guess some or all of the values in a generated sequence. Okay, it should be unpredictable. So we can actually give further definitions of forward prediction and backtracking. So forward prediction is as follows. Knowledge of previously generated sequences should not provide advantage to attacker when guessing the future values. So actually I can give an example here. Assume that you have a random number generator and you look at the results and all of the outputs look random. But all of a sudden, by some inside information, let's say, you realize that these are actually not randomly generated, but it is just the output of an AES encryption. So assume that you chose a counter and a secret key. If you encrypt these counters and increment them one by one, the ciphertext will look like a random value. This is actually what we get from a good block cipher. So if you give all of these ciphertext blocks as randomly generated numbers, then people think that, okay, your random number generator is fantastic. It works in a fantastic way and the numbers are random. But if somehow you know the secret key and the counter that is used in AES for this process, then you can actually guess all of the future numbers that are going to be generated. Of course, I gave a very solid example, but there can be other ways, because if you know how the random number generator works, maybe you can find a weakness and to guess what are the future values will be. Similarly, backtracking is the other way. Knowledge of some generated sequences should not provide advantage to the attacker when guessing the earlier generated sequences. This is also important. Maybe you have a random number generated and you are using it to choose your secret keys. So if you can backtrack, we can capture the previously used secret keys, and maybe we also capture those ciphertexts in the past. This way we can decrypt and obtain the secret information. So unpredictability is very important. These properties is broken in dual elliptic curve random number generator. So this is actually very important, and we will mention it in the future slides. So let's talk about generating random numbers. Generating random numbers with the desired properties is difficult because computer systems are deterministic. This is the main problem. I mean, if you're not looking at quantum states or something, then our classical computers are deterministic. So sampling the seconds value from the system clock is a common approach for a random number generation, but it cannot be used for cryptographic purposes, because if we know at which second, if we can guess at which second you generated that value, we can also capture that value. So this is a very basic way of generating a random number in computer systems, but it cannot be used for cryptographic purposes. Also, using time between the user's keystrokes or mouse movements for an entropy source also do not provide the desired properties. And here we hear a new word, entropy, in this course, so we will talk about it today a lot. So let's give the definition of entropy. So it's the measure of the disorder of randomness in a closed system. The entropy of uncertainty of a random variable x with probabilities p1 to pn is defined as hx, which is the summation from 1 to n with a minus sign at the beginning, probabilities of these values multiplied by the log n of these probabilities again. So here maybe we can give a simple example. Assume that we are generating bits. So n is 2 in our case, because we can either generate 0 or 1. And assume that your random number generator is, working in a uniform way. So the probabilities are 1/2 and 1/2. So here you will have the summation 1/2 times log 2 1/2 plus 1/2 times log 2 1/2 and minus 1 at the beginning. So due to these values, actually you will get, if I'm not mistaken, the value 1. Because 1-bit information has actually 1-bit entropy in that scenario. So I leave it as an exercise for you to calculate. All right. So let's focus on pseudo-random number generators, because we are working on deterministic systems. A pseudo-random number generator is a deterministic algorithm that produces a sequence of random-looking numbers using a seed value. Okay. So pseudo-random number generators have an internal state. So after generating a long sequence of numbers, all variations in internal state will be exhausted, and the sequence of numbers will repeat an earlier sequence. So this is what we call periodicity. So as you can see, this idea looks very similar to stream ciphers, because we have an internal state, and that internal state can have finite values. So after some point on, that internal state will return to its initial position, and from that point on, you will start reproducing the same sequence. So this is what we call periodicity. So as you can guess, we want very large periodicity. But the good thing is that periodicity can be very large, so that it would look virtually infinite. For instance, if your period is 2 to the 100, you will never produce 2 to the 100 bits anyway. So that period will not be a problem for you. So same seed provides the same outputs, hence the property can be used for reproducibility. So this is actually what I use in my experiments. For instance, in an experiment, I need random numbers. So instead of using a random number generator, what I do is that I use the hardware implementation on the CPUs of AES. So I choose a counter, I choose a secret key, I encrypt these counters and obtain ciphertext, and I use those ciphertexts as random values. So in the future, if I need to reproduce those random values, all I need to do is to choose the same counter and the same secret key for AES, so I can reproduce the same values. This way, in my experiment, I can reproduce the same result. So this actually allows you to verify your, experiments by other people, and reproducibility of experiments is really important in computer science, which is sometimes overlooked in academic papers. So most of the time, you only see the results, but since they don't share the same data, or the data set, you cannot reproduce the same result or redo the experiment. If the attacker captures, guesses the seed or the internal state, then the security is lost. So this is the main problem with the pseudo-random number generator. So think about my example. If I use such a seed value to generate random numbers, which I'm going to use as secret keys, if you can guess that seed value, then you can guess all of the future numbers that I'm going to generate. So this actually, from pseudo-random number generators, these are deterministic algorithms, and our computers are deterministic. So from this, this is why we call it pseudo-random. So this actually leads us to the true random number generators, TRNGs. So to avoid the deterministic nature of PRNGs, true random number generators use a physical source to generate random numbers. So idea here is to get the randomness from the nature. Okay, so that is the main idea. So the physical source is called an entropy source and can be physical phenomena like radioactive decay, thermal noise, shot noise, avalanche noise, and Zener diodes, clock drifts, but of course this might be susceptible to timing attacks if you have inside information. Timing of actual movements of a hard disk read-write heads, but actually due to SSDs, now this is kind of an old technology, and it might be redundant in the future if I use it in these slides. Radio noise, and so on. So as you can see here, we are focusing on physical properties of the, maybe the CPU or the motherboard of the computer, and we are looking like we are focusing on things that come from electricity or the heat and so on. So due to their nature, true random number generators do not provide uniformity property because we don't know how a radioactive matter will decay, right? So it will not have the uniform property when we measure these properties. However, a hash function can be used to overcome this issue. So first, get the information from the true random number generator and think it as an entropy source, and then put it as an input to a hash function. The output will have these uniformity properties. So this is one way, but of course, do not forget that true random number generators are not as fast as software hardware solutions. In other words, pseudo-random number generators will always beat true random number generators because you are taking the data from the nature somehow, and the speed of producing those values will be slow compared to this, of course. Yeah, of course, there are other methods. For instance, think about taking a picture. Now, currently, we have a lot of megapixels in these devices, so you can actually use the noise in the picture as a random input and so on. So this leads us to combining these two concepts, which we call cascade construction RNGs. So modern operating systems and cryptographic libraries generally take input from an entropy source to supply a buffer or pool of entropy. Then it is used periodically to see the cryptographically secure pseudo-random number generator, which we call CSPRNG, to provide random numbers. So idea is as follows. So this picture actually explains, for instance, think about a Linux system. The moment you actually turn the power on, the entropy pool actually starts to fill. So think about it like a 4 GB file. So when you power on the computer, it is empty. But during the phase where the operating system starts running, it actually starts to feed information into this pool. So they have an entropy source, actually many entropy sources. They can be the ones I actually mentioned during the true random number generators slide, but also it takes input from, hard drive or your mouse movements, your keystrokes, and everything is fed into this entropy pool. So initially it is an empty file, but once this data comes, it reaches to 4 GB at some point. So you have an upper limit. So let's say that it is 4 GB. Once it is filled, when new data comes, the old actually, deleted. So this way, you always keep the entropy pool filled with new data. And whenever you need a random number, actually, the operating system takes this huge entropy pool and feed it into a hash function like SHA-256, and the result is 256-bit random value. In order to guess that 256 value, you should have the knowledge of this entropy pool, which is a huge file like 4 GB, right? So in order to guess what is inside it, you have to go back and know how the entropy source works. So it is hard to guess these cryptographically secure random numbers. But of course, sometimes attackers try to do this. They try to force the person to, restart their system, maybe because, they performed an update to something. So once you restart your computer, this entropy pool is empty. So if you turn up the system and at that second try to generate a random value, the entropy pool will have some small amount of data. So this way you can somehow try to guess it and guess the random number. So there's this kind of attacks, but it is hard to perform, to be honest. So this method is faster than true random number generators because here we are filling this entropy source from user mouse or movements or keystrokes, hard disk movements, and also the CPU clock and so on, the thermal noise and so on. But this way you generate input in a very fast way. But since the implementation is in software, it is vulnerable to memory-based attacks because you are keeping these data in the memory. Timing attacks. It also does not solve the problem of what entropy source to use. Sampling user behavior is not secure, as I mentioned. If that entropy pool is filled only with your mouse movements, then it is not that hard to guess, actually. So we have some methods, but most of the time we don't have the perfect solution. I mean, we want to have a true random number generator, but putting a radioactive matter and measuring the radioactive decay on your desk next to your laptop is not a feasible method.